Hi everybody. So I'm going to introduce the next unit, energy production and climate change, with a PowerPoint. Not usually my style, but I put this together. Normally I talk to you about this in class. So I just want to give you a little context before we get into the notes. Okay, so what you see before you is a graph. And if it's not clear what's on the graph, we have on the x-axis is time in years, okay? So this is 10,000 before a common era. And here is year 0, at least Anno Dominion, okay? And then year 1000, year 2000. So it's very condensed in time. And then what you want to look here along the y-axis is you see that it got a really low, and then it jumps up, okay? So you can barely tell. So I guess my question is, what is the y-axis measuring? Okay, so as time has proceeded from the last 10,000 years, which is related to the last ice age, up until the present time, or close to the present time here, we see flat and then an exponential rise. Okay, so if you haven't figured it out, let's see if I can get this to work. Yeah, that's the world population. Okay, so our population of this planet has gone from a fairly steady, well, let's take at least since Roman times, right here, roughly, I don't know, 10th or a fifth of a billion of people. And then as we move through the Middle Ages, we're getting to maybe half a billion. And then, I don't know, maybe around 1800s, 1700s, we finally reach a billion. And in the 200 so years since then, we have gone up to 7 billion people. Okay, a staggering rise at an unbelievable rate, especially when you look at how time is stretched out since the last ice age. 10,000 years plus 2,000, so let's call it 12,000 years. It seems like a lot of time, but in the Earth's history, that's, you should know from earth science, is a blink of an eye. So what exactly happened that we jumped up at an exponential rate? Okay, so you might have an idea of that, so I'm going to show you another graph. Here we go. So we see something, now this is not as much time, so this is starting from 1820, so early 19th century to, again, the present time, and we see something very similar, okay? Fairly flat, and then a rapid rise. And that's not population, so we want to take a guess what that is. Okay, well, spoiler alert, let's see if we get to work. That is world energy consumption. Okay, and look at the units, exajoules. I don't even know what an exajoule is. It's a big number, right? I think it's 10 to the 18th. Maybe somebody can confirm that for me. I was too lazy to look it up before I did the PowerPoint. But we consume a lot of energy worldwide. And then in different colors talk about the different sources, which is not the focus right now. Okay, but I guess in a sense it is, because if you look at the biggest amounts, it's the red, this greenish yellow, this violet, which all pertain to that. And those, of course, are fossil fuels. In other words, what happened that our world, the population exploded? Well, around this time, right here, especially with the red, and then basically we discovered fossil fuels. And because of those fossil fuels and the energy content therein, our world changed. And by and large, for the better, okay? Fossil fuels generally have a bad name. It's generally like a 4-letter word, but they've been crucial to our development as a world. And for especially the industrial nations, and even for nations that are becoming more and more industrial. All right. Prior to this time, for 10,000 years, the world was agrarian. It was agricultural. And then when we found this supply of fuel that has tremendous advantages over, let's say, the traditional fuels prior to that, i.e. wood or dried plant matter, we see that things have taken off. So part of this unit, we're going to look at what makes fossil fuel special. What we can talk about energy density, production, and of course what we now know are the environmental issues and other issues that come up with it. Okay, so there's one thing. So I'm also going to show you a third graph. Okay, And again, the point of this is we see flat, 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 and then an exponential rise. And again, from 1700, so the last 200 to 300 years. So what is this? So we've seen a population explosion because of an energy source or sources that have been developed and found. And then concurrent with that is carbon dioxide and other greenhouse gases. So that's another aspect of this unit that we want to look at is when you burn these fuels, especially the three that I highlighted before, you release a tremendous amount of this that's otherwise sequestered, quarantined, if you will, from the atmosphere and even at the surface of the earth. Okay, and so CO2 gets all the recognition, and that's that light blue line here, but there are other greenhouse gases we'll talk about, and if we look at the overall effect, it is also rising exponentially. Okay, so we want to talk about what is the role of greenhouse gases in our climate, and that's really we're going to talk about radiation physics. All right, so we're just progressing along here. So we're going to talk about fossil fuels, what's great about them, what's the downside to them. We're going to talk about alternative fuels, because if we see there are downsides to fossil fuels, especially with the GHGs, the greenhouse gases, we want to look at what can be done to mitigate this, if anything at all. All right, let's move on here. So we can, there are tons of graphs out there put out by government, research, or even NGOs, non-government organizations that look at that. But you can see the contributions of various industrialized nations around the planet. Okay, and it's no big surprise we are the biggest consumers. In fact, I think China has surpassed us in the past decade. So this is probably a little bit outdated. Yeah, so that's 20 years old. But we see, not surprisingly, that a few countries around the world, and we do have the most population, right? India, Japan, and China take up probably almost half the world's population, not quite. And then us with Europe and Japan bring it to about half, but roughly a little more than half. So roughly less than a half of the world's population consumes very little of the energy. So there's definitely a imbalance there. Okay, so the notes will talk more about this, but fossil fuels and energy density. Okay, so energy density, there's two ways you can do that. You can get the density per volume, and that's good for liquids, or you can get density per kilogram, okay, and that's generally what we want for solids. But if we look at the traditional fuels, wood, forest, residues, etc., they're fairly low on here. And then if you look at the classic fossil fuels, gasoline, okay, and its varieties, diesel, biodiesel, right, you're getting roughly, right, 40 or so megajoules for every kilogram you burn. Right here is LNG, liquid natural gas, and propane and ethanol are various ones. We see that's slightly lower than gasoline, and then we see, actually it's pretty much the same, at least in terms of the per kilogram. And we see coal, which has been the traditional one up until recently, the last, let's say, 30 or 40 years, is fairly low compared to the other fossil fuels, but it's much, much higher than wood and even these biofuels that you hear about, burning corn or corn products, or even certain types of grasses that are dried. And then over here is a nice little chart that looks at these from a bar, and then you see that uranium and nuclear energy is completely off the charts. Okay, and so some look at nuclear power production as one way, maybe not the only way, to help us get off of this and take care of not only the finite amounts of the fossil fuels, but the pollution that comes with it. But there are issues with nuclear, but we'll look into nuclear power production, fission, which has been going on for decades, and maybe I don't want to say holy grail, but in the near future, something that seems too good to be true, and that's fusion, and what it entails and what are the ups and downs, or upsides and downsides of that. Okay, so this is just another way of looking at what I just showed you there in terms of mass. So if you burn this much wood, right, 20 tons, you will be equivalent to 6 tons of coal and so on, which is equivalent to 0.57 grams of tritium, which is used for fusion. So that's one of the reasons why fusion is so attractive, is you don't need a whole lot of material to get the same energy as you get from what we burn now. Okay, and that's all, again, towards the idea of energy density. So another thing we'll talk about is renewable versus non-renewable. I think you know fossil fuels are really not renewable. They're fossil fuels because they are plant material and even animal material. And so if you look at how we take plants that die and get buried underground over time, eventually making coal or natural gas or petroleum, right, the liquid and the gas and the solid forms of that, you see that it just takes a lot of time. Okay, I know there's not a time scale along here, but we're talking millions, tens of millions of years. And perhaps the most interesting aspect of this is you need 98 tons of plant material just to get 1 gallon of gasoline. Okay, now gasoline is distilled out of petroleum, so maybe 98 tons gives you, let's just say, 1,000 gallons of petroleum. And out of the petroleum, when we go through the distilleries, not distilleries, refineries, we get gasoline out of that. But you can see, you know, I've read articles over the past decade or so of people taking, let's say, plant material, even roadkill animal, and putting them under extreme pressure and temperature to turn that biomass into fuel. And that's all well and good, but you're not going to get enough for our demands, right? And this conversion kind of gives you an idea of how much you need of the biomass just to give us what we need for running cars or anything else. Okay, so I want to finish up. Okay, so here's world consumption of different types of energies, and I guess we want to talk about, we see that the big three are right here. They've been steadily rising. I think coal has kind of started to taper off, which many would argue is a good thing, unless you live in Appalachia in this country where coal mining is key. And then what we see down here is that the green, or the red, which is nuclear, has been flat for a long time. And we really haven't done much with that. And some would say that's a good thing. Others would say, no, why don't we doing more? So we can talk more about that. But the most important one is the green one. Okay, we want, now again, this graph is, well, it's fairly recent, 2005. We see a steady incline here. What we'd like to see, this is go up while these go down. That is what you see a lot of people talking about. Even in politics now, you at least have roughly one party in this country that seems to be talking about it. How committed they are to it is another issue. Okay, but overall, that's a pretty sobering number. 10 to the 20 joules every year is what we consume as a world. And a kilowatt hour, right, is a unit that you pay energy for. Just to put this in perspective, monthly, when I look at my monthly electric bill, I believe I consume, let's say on average, depending on the time of year, changes 3,000 kilowatt hours per month. Okay, so that's 10 to the 3, where we are 10 to the 14th per year. So if I multiply this by 10 for a number of years, and 12, that's 36, but that's basically 10 to the 4th in my home. And so that's pretty, still a lot, but look at the world value. Okay, so energy consumption by fuels. This is one of the graphs I showed you before. Again, notice the big three dominate here. We're starting to see a little bit other renewables. Hydro's been around for about a century, and nuclear hasn't taken off much. Okay, here is just more of a breakdown of it. I'm not going to go into that. We'll talk more about that in detail. So I just want to finish up is the government put out a really cool website where you can look at any location in the country and look at power plants and whatnot. So I just have a picture here of New York State. But if I click this link right there, I can go to that. So if you want to explore yourself, you can do that. You can zoom in and you can show anything you want about energy production. I wish I had more time now, but maybe in class I'll show you.